So we want to talk about the four main categories of solids that the quiz question was asking about, and what makes them different from one another, what similarities they have, what's happening with the individual particles inside of the solids that gives them the properties they have. So again, we're using our understanding of how atoms and molecules behave to explain the properties that they display that we can measure in the lab and observe with our eyes. So first category here that's discussed in this section are covalent solids. These are often called network solids. And what sets them apart from other solids is that you have a network of covalent bonds, three-dimensional network, and all of the attractions between the atoms in this solid are covalent bonds. Right, so we have a sense for what covalent bonds are and how they work. We know that, for example, carbon needs to be stable and needs a noble gas configuration. So generally these nonmetals will share readily with other nonmetals like carbon or hydrogen, oxygen, nitrogen. Right? So that's how we make molecules, because molecules, for example, like if I just put a hydrogen at each one of these positions, a molecule is a discrete unit with a specific number of each type of atom, and I need that number of hydrogens and carbons to make all the noble gas configurations, to make it stable, right? To give it noble gas configurations and avoid a lot of formal charge, unnecessary formal charge, to make the molecule stable, right? So that's a molecule. A molecule is a group of atoms that are all sharing electrons in some way. A covalent solid is a little bit, well, actually, a covalent solid is a molecule. It's just a huge molecule where all of the atoms are sharing electrons, and they're extending this network of covalent bonds or shared electrons in all directions three-dimensionally. So instead of having a discrete small molecule like that only has a few atoms, you have a network. So here every carbon is bonded to four other carbons in a diamond. And in your pencil you actually don't have one molecule, but you have layers where all the atoms in this flat layer involves carbons bonded to other carbons. So what makes this a covalent solid is that covalent bonds are holding all the atoms together. So, see, if you think about a diamond, one individual diamond is one molecule. Right? Because all the atoms are sharing electrons. So what would it take to break that up? If I wanted to cut a diamond or burn a diamond or melt a diamond, well, I would have to break up a bunch of these covalent bonds. It's very different from melting or burning or cutting a molecular substance like water, right? Because in water, the water molecules can maintain all their noble gas configurations and avoid formal charge even when I separate the atoms of one molecule from another molecule. Right? So because the molecules are discrete numbers of each type of element sharing electrons, I can separate one molecule from another molecule without breaking any covalent bonds. I don't have to break any noble gas configurations to do that. But to break up a diamond, I do, because in a diamond, this carbon atom here is bonded with four other carbon atoms. It needs those bonds to maintain its noble gas configuration. And if I want to cut it, or burn it, or melt it, I've got to allow atoms to move away from one another. They have to break covalent bonds to do that. Right? So if the whole thing is one molecule, the only way to break it up is by breaking covalent bonds. So in a covalent solid, to melt or burn or cut, covalent bonds must be broken. Some covalent bonds are stronger than others. But generally, covalent bonds are pretty strong attractions because they're needed to maintain the noble gas configurations. And if I break them, the molecule will become really unstable because it will start to break the noble gas configurations. It might create some formal charge. And so all the electrons are held into these bonds between the atoms real tightly. It's hard to break that up. So when everything is held by covalent bonds throughout the entire sample, that's a covalent network solid. In contrast to that, if I have discrete molecules that attract to one another through intermolecular attractions, then I have a molecular solid. So in this case, I have individual water molecules. So there's one right here. Right, this individual water molecule has one oxygen and two hydrogens. It's not connected to other water molecules through covalent bonds, right? This is not the way it looks. I don't know why I put an X there, but it doesn't really matter because it doesn't exist anyway, right? Hydrogen's not going to have two bonds, right? So it's not a covalent solid. Even though there are covalent bonds present holding some of the atoms together, a covalent solid is where all of the atoms are connected to one another through covalent bonds. And covalent solids are usually very hard, very difficult to break up because those covalent bonds are really strong attractions holding the atoms together. In a molecular solid, the attractions that hold the molecules together are covalent bonds. That's strong. But to hold the solid together, you need not only the attractions that hold the individual molecule together, but to hold the solid together as a solid, all those molecules need to line up, and you have to have attractions between the molecules as well. So in this case, the attractions between the molecules are the van der Waals forces, London forces, dipole-dipole attractions, hydrogen bonding. So between one molecule and the next, that's what the blue lines here are meant to show, intermolecular attractions. And so intermolecular attractions are generally partial charges. So in this case, the water molecules are only attracted to one another not through covalent bonds, but in this case hydrogen bonds, or in other examples of other molecular solids, maybe just dipole-dipole or maybe just London forces. So I just have a weak attraction between opposite partial charges, and since that attraction is not necessary to maintain noble gas configurations, it's relatively easy to break. So it doesn't take much to melt water. If you have ice, it doesn't take much energy, right? Because all you have to do is put a little energy in. The molecules start to vibrate faster, they start to move a little bit, and then that motion is enough to overcome the weak attractions. The hydrogen bonding, dipole-dipole, London forces are weak attractions relative to covalent bonds and ionic bonds, which are much stronger attractions. Right? So the properties of the solid depend on the types of attractions that are required to keep it in the solid state. In a molecular solid, intermolecular attractions are required to keep it in the solid state. In a covalent solid, covalent bonds are what's keeping it in the solid state. So it's a big difference in the strength of the attraction. Did you have a question, Rachel?
Yeah,
Sure. Sure.
why does the graphite break so easily?
Oh, that's a great question. Yeah, that's a great question. So, probably should have mentioned that. So, in graphite, technically, it wouldn't really be considered a covalent solid because it's not completely connected through covalent bond. So in graphite, if you look at carbon likes to make covalent bonds to make a noble gas configuration, and we see carbon bonding a lot in rings, especially six-membered rings. Put some double bonds in there. So if I look at that ring, how many more bonds does each carbon need to be stable? Each carbon already has 3 bonds, so it needs 1 more, right? So if I put 1 more bond to 1 more, I can see that I can start to extend this into a sheet. And so if I fuse these rings together in sheets, I ran out of space there, but keep going here, and I keep alternating these double bonds throughout the sheet, and I extend that sheet in all directions, making a flat sheet. That's called graphene, which is just 1 sheet of carbons bonded together. Graphite is then when those sheets stack on top of one another. So an individual sheet is a covalent solid. An individual sheet of graphene, everything's connected through covalent bonds. That 1 layer of carbon atoms are all bonded together, right? That's what they're meaning to show here. So this layer is coming out at you. The carbon atoms are all sharing electrons. But in your pencil, 1 sheet lies on top of another. From 1 sheet to the next, there's no covalent bond holding that together. So this is it's really an example of something that more fits a molecular solid. But because we have this long-range extended network of covalent bonds, it can also be considered a covalent solid sort of at the same time. So it's kind of like it has characteristics of both. So it has characteristics of a covalent solid because within that 1 sheet of carbon atoms, you have a large, long-range network of bonds that extend throughout, holding it together through covalent bonds that are needed to keep the noble gas configurations. So that 1 sheet is a really strongly held together. And so if you took just 1 sheet of carbon atoms and tried to stretch it, it would be very difficult, very strong. And if you put that 1 sheet of carbon atoms and just laid something on top of it, it would hold it for the most part because it's going to maintain those covalent bonds to stay connected. There's really strong attractions holding it together. But the attraction from 1 sheet to the next is not strong because it's not a covalent bond. What type of attraction do I have between this layer of the graphite and that layer of the graphite? Yeah, London forces, dispersion forces, right? Because this carbon bonds are nonpolar. So the only reason this sheet would attract to that sheet is if the electrons just temporarily, randomly shift around and create instantaneous dipoles. So I get some instantaneous dipoles forming all over the sheet, all over the bottom and the top of the sheet. I get these temporary partial positive and negative charges forming constantly. So that allows 1 sheet to attract to the next. And those attractions are what you need to keep it in the solid state. But when you write your pencil graphite, it has these layers stacked on top of one another, and 1 layer is not really connected to the next through a covalent bond. It's just slightly attracted through these temporary partial negative and partial positive charges. So when you slide your pencil across the paper, the sheets stick to the paper as well, and they just slide off of one another and just start to get deposited on the surface of the paper. So it's soft because the attractions between the layers of graphene are not very strong, but the graphene layers themselves are really strong. Good question. Other questions so far?
Why does the diamond look sort of like a disorganized structure?
That's probably just the perspective. Because it's 3-dimensional like that, it's really hard to show it on a 2-dimensional paper, making it look completely organized. But if you look at any, it's really hard to see from this angle, but if you pick out any one of these carbons on the inside of the diamond, it's tetrahedral. And so it has 4 bonds to 4 other carbon atoms. And its surroundings look exactly the same as any other carbon that you choose on the inside of the diamond. So that is a great structure for carbon because it allows each carbon to have 4 single bonds to make this noble gas configuration, and all the bond angles are just right. You get the right geometry, so it has a really high stability for that reason. And it's highly organized as well. So that's another thing we see for most covalent solids, but not all, generally they're crystalline. Because if they're held together by these strong covalent bonds, usually that means that they have to be organized in order for the atoms to be in the right places to make the right molecular geometries when they form all these covalent bonds. So in contrast, molecular solids, there are covalent bonds holding the individual molecules together, but what holds the solid together are the attractions between one molecule and neighboring molecules. And those are weaker attractions. So it's easier to melt them, it's easier to get them to flow around. And we have different properties. It's not going to be as hard a substance, it's usually a much softer substance as a result of that situation. So there are way more, so these are way more common too. Very common. There's tons of molecules that exist. Because carbon is so prolific in its ability to bond to so many different things in so many different ways, there are millions of different molecules that are different combinations of carbon with other elements. That's why we have a whole area of chemistry that just revolves around carbon, which is organic chemistry. And those molecules, a lot of times, they are, the molecule will have some specific shape. If it's got 10 carbons and 15 hydrogens, whatever it has, it'll have some specific shape, and that will allow it to form some intermolecular attractions with the neighboring molecules, and they'll line up usually in a crystalline arrangement. So these are very common. They're usually crystalline. The crystalline versus amorphous analysis usually revolves around the shape of the structure, the shape of the particles that I have to pack in and try to organize. So like we said last time, anything that's small and regularly shaped, meaning that each particle has the same shape as the next, will be pretty easy to pack in an organized way. And since the molecules do form attractions to one another, often there is one best way to organize the structure to make those attractions. And water is a great example of that, because if you look at one of the water molecules, it's hard to see here because it's kind of small, but if you look at one of the water molecules on the inside of this structure, it has 4 hydrogen bonds to 4 neighboring water molecules. And the organization of that structure is required to allow that water molecule to be placed next to 4 other water molecules in 3-dimensional space with just the right distances and just the right proximity to make those hydrogen bonds hold it together. Questions about that? Okay, so third type of solid is a metallic solid. These solids are just made out of metals, so it's very easy to recognize. A metallic solid would just be either a pure metal element from the periodic table, or an alloy, which is a solution of metals that when it hardens it turns into a solid where you have different metal atoms mixed in with one another. But what do we know about the metals we talked about already this semester is that metals have loosely held outer electrons. So since they have loosely held outer electrons, when they get next to other metals, they create really powerful London forces, or the equivalent of London forces, where the electrons can really shift around and move from one metal atom to the next. Okay, so normally when we think about an atom anyway, we think about it having a tiny, tiny positively charged nucleus, and then the electrons are soupy. Right? We saw that demonstration where if I move the nucleus, the electrons just kind of like morph around, and they can flow around the nucleus and attract to that positive charge. So the more metals usually have more soupy electrons than nonmetals, because metals have usually a significant amount of shielding to repel their outer electrons, and not very many protons in the nucleus compared to the nonmetals on the right-hand side of the periodic table to pull the outer electrons in. So their outer electrons aren't held very tightly. Those outer electrons are especially soupy, and they shift around very readily. So when metals get next to other metals, the gray area here is meant to show the electron cloud. The electron cloud of one metal will overlap a little bit with the next metal. So it's not like a covalent bond, because the electrons between those nuclei, they don't have to just necessarily be in here. The negative charges, the electrons, they don't have to be in there to make the noble gas configuration for the metals. They just are loosely held by one atom, so they're susceptible to being attracted to the positive charge of the neighboring atoms. And so what I create here is like a sea or ocean of electrons that flows readily over the entire sample of all the nuclei. And that holds the nuclei together, right? So if you're an electron, what's your main goal in life? Yeah, to attract to positive charges. You have a very simple life. So to attract to a positive charge, you want to attract to as much positive charge as you can, because you're negative and you attract to positives. So if you have this network of positive charges and you're an electron and you're not really that tightly held by the positive that you started with, as an electron you can go anywhere. You can move throughout here, go to any atom, and so I have easily flowing electrons over the entire sample of this entire metal. The whole thing has soupy electrons over all of it. And so in effect, each individual electron can really kind of attract to all the nuclei at once, because it can move anywhere and be attracted to all those nuclei. So that really helps to it holds the whole thing to metal, and the whole thing together, so that the electrons can continue to flow. Because if one of these metal atoms drops out, or if I cut it off of the surface, then its electrons can't attract to the other atoms anymore. The electrons are just stuck around that one atom. And so that's the property of the particles, the way they behave, that explains a lot of the properties of metal. So delocalized means they can move around easily. They're not localized. They're not stuck in one location on one individual atom. It makes them good conductors, right? To conduct electricity, we haven't really talked about this yet, but electricity ultimately, to be conducted or to flow, if you want electricity to flow from one thing to another, you need charged particles that can flow. Right? So electrons are charged particles. So when we think of electricity, most of the time we think of electrons flowing through some piece of metal. Right? So if you have an electrical device or a battery or an outlet in the wall, that has electrons that are kind of built up and ready to go. And if they move from one side of a battery to another, or through a wire from one part of the outlet to the other part of the outlet, they're flowing through there because they're attracted to the other side. And that flow of charge through that device is what electricity is. So metals are great at conducting electricity. If I bring a bunch of electrons in, a flow of electrons, and they come in here, what's going to happen to the other electrons that are already in the metal? Well, these other electrons that are here are going to be repelled by the new ones coming in. They're just going to shift over. That's going to cause this electron to shift over, this electron to shift over. So you kind of have like a parade of electrons, or like almost like a domino effect, where one electron knocks into the next and pushes it onto the next atom. That pushes it onto the next atom. So it's very good at allowing electrons to flow through the metal quickly. When you think about electricity, you don't think about the new electron like making its way through here and flowing to the other side. You think about as soon as it comes in, it just pushes the next one over one atom, and one pops out the other side like almost immediately. So that's why electricity is able to flow through metal so quickly. This is also generally going to be crystalline, because these are usually small atoms, spherical shape, regular shape, easy to pack them in an organized way, and allow the positive charges to be kind of separated from one another, and allow the electrons to get between the positives and flow around all over them.
When it says
Yeah, that would be if your metal is pure.
So if you had an alloy, how would that?
So if you had an alloy, you might have a different quantity of positive charge on some of them, and then that might attract electrons a little bit more than some of the other atoms. Depending on how much of that other metal was mixed in, it would affect the properties a little bit. So some metals, the metals that hold their electrons more tightly than others, are going to have slightly different properties. So if you mix metals together, you can kind of customize the properties to an extent. Oh, the lattice. Lattice refers to the way that the atoms are organized. So a lattice point is just every atom is creating a point that describes the distance between the units in that organized structure and where the units are in that organized structure. So a lattice point is just each individual point in the organization.
And that like specifically in an alloy, if they're not, if each point isn't an atom of the same metal, it could be like a molecule or a mixture of two metals.
Yeah, so when you make an alloy, you mix the metals together homogeneously. So it'd be completely random and thoroughly mixed. So if I mix like zinc and copper together, if I had like 80% zinc, 20% copper, then I would just randomly pick 20% of these and make them copper, and the other 80% would be zinc. It would be completely random and completely thoroughly mixed. So usually when you make an alloy, it's a homogeneous mixture, so everything is thoroughly mixed, and there's no way to necessarily predict and say like every third atom has to be a zinc or something like that, because it would just be randomly mixed in. Okay, so this one kind of summarizes the ones we've talked about, and we already talked about ionic solids already in an earlier chapter, so we'll maybe just review that briefly. So an ionic solid usually exists when you have a metal and a nonmetal, or a group of nonmetals mixed together, right? Because the metal has loosely held outer electrons and they're easily pulled away, and often in nature they're already found with their electrons pulled away, so they'll take on some quantity of charge, maybe a +1 or a +2 or something like that, up to +3 or +4 maybe. And the nonmetal needs to make a noble gas configuration as well. The metal will lose electrons to make a noble gas configuration usually. The nonmetal will gain electrons to make a noble gas configuration, so it might have a -1 or a -2, depending on what the nonmetal is. And then the reason they come together is because opposites attract. So this substance, the individual atoms exist as charges usually to make their noble gas configuration. What holds the solid together are ionic bonds, full charge attractions between ions, fully charged particles. Right, so if we were to think about how strong those attractions are, would we normally expect ionic substances to have higher or lower melting points than molecular solids? Yeah, much higher, right? Because in an ionic solid, which is pretty much always going to be crystalline, you have opposite charges, and so those are pretty strong attractions. If I want to melt that, I've got to break those attractions and allow the ions to flow around kind of independently like a liquid. They have to flow past one another. And so that takes a lot of energy to get them moving fast enough to slide past one another when they have full charges holding them together. In a molecular solid, the only difference is in a molecular solid, all my molecules are usually not fully charged. So I would have neutral molecules that only attract one another because maybe they have a dipole-dipole, partial charge attraction, or maybe a temporary dipole, London forces, or maybe a relatively strong dipole-dipole known as a hydrogen bond because I've got a hydrogen with a large partial positive and a large partial negative on an electronegative atom. Even so, though, I still have only partial charges, so it doesn't take much to break those attractions and get these particles to flow around independently. So the melting point is usually much lower. Right, so what we can say is ionic substances have the possibility of conducting electricity, and this was a point that some of you kind of overlooked a little bit on the quiz. Many of you recognize that ionic solids can conduct electricity, but when they're in the solid state, it's really not easy for them to do that. Right? So when we saw the metallic solid, as a solid, a metal can usually conduct electricity quite well because then flowing electrons, and when new electrons come in, other ones pop out the other side. The electrons or the charged particles can flow right over that surface very easily usually. So to conduct electricity, I need charged particles that can flow, that can move around. And in an ionic solid, I have charged particles, but they can't really flow because they have to stick together to maintain their charge attraction. Their ionic bonds hold them together. The opposite charges keep them in place. So as a solid, an ionic solid generally doesn't conduct electricity well. But if I melt it, it will, because now I have the ability for the ions to flow and move around. Or if I dissolve it, and one of the best solvents to dissolve ionic substances is water. And so what water will do is it will allow the ions to separate. The water molecules will surround the ions to keep them apart. Then the water molecules will have, some partial charge to attract the ions. The partial positive will line up around the negative ion. The partial negative will line up around the positive ion. And we can form anywhere between 4 and 6 partial charge full charge attractions or ion dipole attractions to make up for the fact that we broke this one ionic bond between the full charges. But now that it's dissolved and the ions are independent, we've got new partial charge attractions to help stabilize them and keep them apart. Now they can flow away from one another, so now I can actually conduct electricity. So you need charged particles to conduct electricity, and they have to be able to flow around from one area to another. So our ionic substances are held together by Coulombic attraction, which is really just ionic bonds. They're usually hard because those are strong attractions, require a lot of energy to break. They're lined up in an organized way, so if I do have enough force in one spot, usually you can crack that open along that line of attractions, so that makes them brittle to a degree. They have very high melting points because it takes a lot of energy to move the charges away from one another since they're very strongly attracted. They're poor conductors of heat and electricity because they're held together so tightly they can't flow around. They don't vibrate too much because the attractions hold them together tightly. So they don't conduct heat or electricity well unless you dissolve them. Then they do conduct electricity because now the ions, or melt them because now the ions are free to move around. And we recognize them usually because it's a metal and a non-metal. To recap, covalent solids or network covalent solids are held together by a network of covalent bonds. That's what's holding the solid together. And so it takes a lot of energy to break those and break it up. So they're very hard, just like ionic substances. High energy required to break them up. Very high melting point. They have very poor conductivity, right? If I think about to try to conduct electricity over a covalent solid, that's not going to be easy to do because in a covalent solid, all the electrons are held in these bonds. They need to be there to make the noble gas configuration. So I can't really put new electrons in because all the electrons are held tightly in the positions they're in. They can't really flow to the other side like they can in a metallic solid very easily. So generally, all of these properties are general. There are exceptions, but for the most part, we can say something about the behavior of these solids based on the particles that are involved and the attractions between those particles. So molecular solids have much weaker attractions that are holding the solid together. There are covalent bonds, but those are not necessary to hold the solid together. They're just holding the individual molecules together. The molecules attract to one another through much weaker attractions. That's what makes it solid. And so since they're weaker, it doesn't take much to cut them. It doesn't take much to melt them. However, because the electrons are still held tightly within those orbitals around individual atoms to make their noble gas configurations, they can't really flow onto other atoms. So I still have a poor conductivity, poor ability for electrons to flow over the surface of the solid because the electrons are held in position to make the noble gas configurations of the molecules that those electrons are associated with. Any questions about those? Okay, so just to mention a little bit more about amorphous versus crystalline. So most substances that you'll come across are going to be crystalline, because most of the time, if you have a pure substance, every unit of that substance will look the same. So if I have pure water, every molecule is H2O. And as long as the molecules are relatively small or rigid, or every molecule has the same shape as the neighboring molecules, then they should pack in an organized way to maximize the number of attractions they can make with one another, right? Because they really want to do two things. They want to get close together, because if they have even weak attractions, they want to be right next to one another so those attractions can take hold and hold them together. And they want to maybe line up if necessary so oppositely charged ends can be close together. Right? So they want to be close and they want to be lined up. That suggests that then most of the time they'll be organized. They'll mostly be crystalline. But amorphous solids usually form if you have a structure that lacks a regular three-dimensional shape. So if I have, instead of like a spherical structure which packs well with other spherical structures, and that would usually be a crystalline structure, maybe I have floppy molecules that are not rigid, and maybe they have like the ability to bend and flop around like spaghetti noodles. In that case, one molecule is going to be, at any given moment, it's going to be in a different rotational conformation or a different flip-flop way of forming than another molecule which might look more like this or something. So how do I start to pack those molecules in an organized way when each molecule at any given moment is shaped differently from the rest because they can bend and flip-flop in different ways. So you usually see amorphous if the molecules don't have a regular shape, meaning they're shaped differently from one another. Glass is a really interesting substance. It has some unusual properties. So we'll take a look at glass a little bit since it's such a common substance. Glass is an unusual because it's amorphous most of the time. Most glass is amorphous. If you want to get crystalline glass, it's much more expensive. But amorphous glass is a bit surprising because glass is a covalent network. And most of the time when we think about a covalent network, if the silicon and oxygen that make up glass are bonded together, and then that's bonded to another silicon, which is bonded to more oxygen, to make this organized, normally you would think that would have to be, in order to make all the covalent bond connections between all the atoms, it would make sense that it should be organized so that they can keep the right molecular geometry and avoid the angles being the wrong angles and make all the electrons share in the right way between the atoms. But it depends on how the glass is made that determines how crystalline it is, and it also depends on whether there are impurities present. And so you can definitely imagine if you put something in here that's a different substance that other than silicon and oxygen, like alumina or this boron or something like that, those areas where you have something different is going to organize in a different way from the areas that are pure. And so that can kind of break up the organization. So depending on whether you need it to be crystalline or not, which you wouldn't unless you're working in science and you need it to be very specific properties, most of the time glass is going to be amorphous. So this gives you a sense for the difference in the organization, right? So here we have silicon and oxygen. And so if you have impurities, or depending on how the glass is formed, it most of the time will form an amorphous structure, which means that some of the bonds might not be completely well formed, right? So if this silicon atom can bond to up to 4 oxygens and it only has 3, it's not going to really be as stable. And when it's unorganized or it's disorganized, you don't have everything set up and lined up in the perfect arrangement to form the maximum number of attractions often. So it's not going to be quite as stable. If you organize glass and make it into crystalline quartz, then each silicon can have the right number of bonds with oxygen, and everything can organize in a way to maximize all of the attractions. But it takes a specific way of making glass to be able to do that. So you should be aware that glass can come either way. It depends on how those covalent bonds are kind of locked into place when the glass is formed. I wanted to mention a couple other things about this section involving solids. So one thing is that you can also do something called cross-linking, which is very common in material science. Cross-linking is a way of making a molecular solid into a covalent solid. And this is used a lot. It's used in the vulcanization process that makes automobile tires. It's used to make hydrogels, which are used a lot in medicine, and they're also used in soft contact lenses. So there's a lot of things that involve cross-linking. It's also a process that is used to harden the ceramic that they use now for tooth fillings. So if you go to the dentist and you get a filling, they put that like paste on there, and then they shine a UV light on it. The UV light initiates the cross-linking process. So cross-linking is where you take individual molecules, like in a molecular solid, you have discrete molecules that are attracting through intermolecular forces, and then you link each of those discrete molecules up with the neighbors through covalent bonds. Right? So if I've got a few molecules, maybe they're like some chains, molecules have chains, that's a molecular solid. Right? But if those chains have sites on them that are still reactive, and I can use UV light or some other chemical reaction to connect one chain to the next, and then I connect on other sites to neighboring chains, now I can connect this molecular solid, everything's connected together. So now I have a covalent solid. So cross-linking affects the properties of the solid, right? If we go back and think about what were the properties of molecular solids versus covalent solids. Molecular solids are often soft. It might be like a paste or a gel or something like that. And then if I can connect the molecules to one another, I can make it covalent, which will make it harder. Right? That's what works for your tooth filling. That cross-linking process makes it harder. Or the cross-linking might make it so it's not dissolving in water anymore, and that's how hydrogels work. And so if we think about before the cross-linking process, that these individual chains were dissolving in water, right? If this was a solid and the chains are all close together, if I put it in water, the chains can separate from one another and get surrounded by water molecules and dissolve in water. But once I cross-link it, it can't do that anymore, because now the chains are connected by covalent bonds. So the chains can't slide past one another anymore. So I make a hydrogel, because now instead of the chain separating and dissolving in water, the water will move in here and fill in these gaps between the chains, and the hydrogel will swell with water and it'll become like a contact lens. If you ever have a soft contact lens and you leave it out of solution, what happens? It dries up and it gets super, super tiny. It looks really, really small. Most of the mass of that contact lens when it's in solution is water, because the water molecules go in there and attract to these chains. And the chains are cross-linked or connected to one another, so they can't dissolve in the water, but the water moves into the hydrogel and kind of swells it up. So there's a way that you can make a molecular solid into a covalent solid. It's called cross-linking.